So in the third step, we are going to combine the plot from our step 1 and 2. So we'll consider as the first scenario where we have the first reactor being the CSTR small, and in the next step we would have our CSTR big. So if we sketch it, here we have our small reactor, here we have our big reactor, and here we have our flows, here we have our entering conversion A0, here we have the conversion A1, leaving our small CSTR, and exiting our big reactor, we would have the conversion A2. Here we have our graph. On our y-axis we have negative RA, and on the x-axis we have the conversion of the species A. So from 1, we determine that negative RA is equal to K times CA0 times 1 minus conversion of the species A elevated n. Now let's assume a first order reaction order because we can sketch it more easily. Here we have our linear relationship. Here we have conversion of the species A0, which is 0, and the maximum possible conversion for species A would be 1. And from 2, we have derived that negative RA is going to be equal to 1 divided tau of the reactor I times CA0 times conversion of species A I minus the conversion of the species A I minus 1. So if we start off with the small reactor, we start off by conversion A0, and here we would have our linear slope, and the cross section would lead to our exiting conversion A1. So here we have the slope, which is 1 divided tau small times CA0. And with this conversion, we would enter our big CSTR. So this would be the entering conversion for the big CSTR. And here we would have a slope which is smaller than the one we would just watch before. And here we would have our exiting conversion A2. So here we would have the slope 1 divided tau big times CA0. Now we will use slightly different colors, but I'm meaning our same reactors. So here we have our same big CSTR with a lighter red. And we would put our small CSTR in a lighter blue color. In the next steps, here we would have our entering molar flow rate A0. Exiting our CSTR, we would have our conversion A1. And leaving our small CSTR, we would have the conversion A2 for this specific arrangement. So here we had our previous arrangement. So now we will start with the big one, and this has the same slope because we had the same reactor. However, we're starting off with the conversion A0 being equal to 0. And this cross section will lead to the conversion A1. And from here, we would use our small reactor, which would have this exact same slope, with the difference that our entering conversion would be conversion A1 from the big CSTR. And if you cleanly plotted this, unlike me, you should actually end up with the same final conversion A2. So, what is our conclusion? So for n equal 1 as a reaction order, or first order reaction order, the arrangement of small and big CSTR, so the order, does not matter in regards to the final conversion. However, if n is not equal to 1, so n unequal to 1 reaction order, the order will affect our final conversion. So let's say our reaction order is bigger than 1. So here we have our negative error A on the y-axis and the conversion A on the x-axis. And the curve of the reaction will look like this. Let's say we have first our small reactor with this slope, entering with conversion A0 being equal to 0. Here we would have our conversion A1. And from here we would use our big CSTR. And we will end up with conversion A2 here. So if we would first have used our big CSTR, and so these two are parallel, we would have conversion A1 here. And if we would have used the small CSTR afterwards, we would have a conversion A2 here. So conversion A2 for the arrangement where we have the small reactor first and then the big reactor is going to be bigger for the other arrangement. So here you always have to take a case-by-case analysis before determining which order is actually best suited as in terms for the conversion leaving your system.